Hello, hello. Hey guys. Good, how are you?
It's like a lot of back pain.
I've been having a lot of back pain the last few weeks. All right, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Good.
Good, good. All right, you guys turned in your midterm projects on Friday. Is my mic too loud? How's it on Zoom? It looks like my mic's going crazy. Is it okay? Is it okay on Zoom? It's a little loud. Okay.
Loud.
I'm not sure how to fix that. Let me see. Okay. Yeah, I guess you guys can turn it down. Although I guess for the recording, it's going to be very big. Let's see. Output level, input level. Here we go. Come on.
Oh, it might need to check off the automatic adjust.
Yeah, let me try that. There we go. Okay, is that a bit better? A little bit less loud? Okay, good. Okay. Anyway, I'm back to the beginning here. All right, so on Friday, you guys turned in your midterm projects. So from the ones I've seen, you guys have done a great job. Okay? And so the next step for your project, which is going to be the subject for the final project, is to run a computational fluid dynamics simulation. Okay? So this is timed actually pretty well with the class because we've been kind of working our way up through all the different modeling methodologies, and so we've done lump parameter networks, we've done 1D equations, we just got done doing 2D stuff, and so that's the Wormersley profile. And so the next logical step is to do 3D flow modeling. But unfortunately, 3D flow modeling is so complex that we have to rely on computers to do it. Okay. And so that's what you guys will be doing for your project. And so today, what I want to do, and we'll see how far we get. We might have to do this on Thursday too, is just to kind of introduce the concept of computational fluid dynamics to you guys. Okay? And so, I know CFD is probably a term that's kind of thrown around a lot, among students. I know when I was a student, it was that really cool thing that everyone wanted to do. Everyone wanted to do CFD. Okay. And so, I wanted to kind of define what it is today, and show you that it's not just a magic button. Okay. And so I get this a lot, because I teach a lot of the classes in this department that has to do with computational simulations. So we have this class, we have finite elements. There's 417, and so people kind of have this impression that simulation technology is just kind of, you make a model, you give it to a computer, you push a button, and then magic happens. Okay, there's a lot that actually goes on, in terms of actually setting this up properly, because there's a lot of things that you can do incorrectly with these simulations that lead to obviously results that are not good. Okay. And so if you haven't taken a course like finite elements, if you haven't taken a course like 417, don't worry about it. We're going to go through all the basics of running, not just a CFD simulation, but just computational simulations in general. Okay. And so that's the announcements. Oh, another announcement, probably the most important one. We have a midterm exam, and so our midterm exam is going to be next Thursday, and so I believe that's April 28th. Okay. And so yesterday, you should have seen me sent out an email that has the study guide for the upcoming midterm, as well as a poll. Okay. So this will be the only exam that we take in this class. And if you haven't taken an exam with me before, usually my policy with the exams is to only test you guys on things that we've covered in the class, which seems obvious, but not every professor, I think, follows that doctrine. And so to help with your studying, I prepared a study guide to kind of help. Okay? And all that study guide is just a summary of all the learning objectives we've gone over in the class. But what I always tell people is to always start with the study guide and use that to guide your study. Okay, that's why it's called the study guide. And so this class is unique because we've done very little actual problems and very little actual calculations. And so a lot of what we've been learning is conceptual knowledge. And the exam is going to reflect that as well. Okay, so I believe I sent in the email the format that you can expect for the exam. And so it's going to be 80% conceptual questions. And so questions that you would answer, 2 or 3 sentences. And there's going to be one lump parameter network problem as well. Okay. And so it's quite a lot of content, because we haven't done an exam yet. It's basically, the entire semester up to this point. So it's in terms of the amount of content that's there, it's almost like a pseudo final, just because it's occurring kind of pretty late in the semester as well. But again, a lot of that is conceptual stuff. And, and I write my study guides in such a way that if you can answer all of the learning objectives on the study guide, you're going to be in great shape for the exam. Okay. So, what most people do, what a lot of people do in my classes, they go down the study guide and they just go, learning objective by learning objective. And, they just make sure that they know that stuff. And so if you can do that, you're going to be in great shape for the exam, especially this one, because it's mostly conceptual. Okay. I also record review videos. And so, I know that, especially for this one, because we've been going so long without the exam, it's always useful to have kind of another video or another piece of content that you can use to help you study. And so I plan to record the review video probably Friday afternoon. That's the kind of the earliest I have some free time this week. And so if you notice in the email I sent yesterday, I also put out a poll where you can vote on the topics that you feel most uncomfortable with. Okay? And so just based on the sheer amount of content that there is on this exam, I can't cover absolutely everything on the review video. And so I want to make sure I focus on the topics that people want to see. Okay? And so of course, we have all the lecture recordings in the class, you can refer to those. But watching all the lectures again, even if you do it at like 1.5 speed is not a productive way to study, I think, for the exam next week. And so, what I've seen is that, having a review video, I usually take about an hour for the review video. That's usually something that's really helpful to kind of shore up on those topics that people feel most uncomfortable with. Okay? And so please make sure you vote in the poll on Friday. It's not, or by Friday, it's not required, but, of course, the more people that vote, the more useful it's going to be for people. Okay? So you're not graded on it, and I don't even see your names on it. I don't see who completes it, but, of course, those things are more effective the more people vote. Okay? And in terms of the exam itself, it's going to be an in-person exam. And so, everyone has to come to the lecture. And so there's no plans to offer the exam virtually. And you are going to be allowed to bring one single 8.5 by 11 sheet of notes with you. Okay. And so besides that, the exam is closed book, closed notes. And so the only thing you can bring is just that sheet of notes, your writing utensil, and a calculator. Okay. You probably won't need a calculator, but I know for me, when I was a student, my TI-84 calculator was like my security blanket. So I always like to keep it with me just for good luck, even though I didn't use it for half the exams. Okay, and so that's the exam. Okay, and so definitely get started studying on that. And if you have any questions about anything, just as always, I'm always available for you. Okay. That's all my announcements. So are there any questions I can answer before we get started? Yeah.
Yeah, the cheat sheet, are allowed to print it?
Yes. Okay. Yeah. My only requirement for the cheat sheet is that you can read it, and so no size 2 font, and you can't bring magnifying glasses, and so that's what I always tell people. And so as long as you can read it, you can even do like the Ken Jeong thing where you like that thing. As long as you can read it, that's fine. And so, but no weird stuff. And also, you obviously can't put the exam answers on the cheat sheet, but that's going to be impossible. So don't worry about that. Okay. All right. Any other questions on the exam or anything? Okay. All right. So let's go ahead and get started. Okay. So this set of lecture slides that I have is about computational fluid dynamics. Okay. And so this is kind of your introduction to simulation technology, right? And so if you've taken a simulation-based class with me, maybe you've taken finite elements, you'll see maybe some repeat information here. But if you've never taken a simulation-based class, then this should get you up to speed. Okay. And I will say that the theory behind these kinds of solvers is very intense, right? So we're not going to go behind any of the theory, but there's at least some practical knowledge that you need to actually use the tool. Right? It's just like any tool. And so that's what I always tell people, that simulation technology is really not that different from any tool that you would use in machine shop, right? So you have like your mills, you have your lathes, right? Simulation technology is just another tool. And so just like, before you use a mill, before you use a lathe, you have to have some basic knowledge about how it works and safety. Simulations are the same way. Okay? And so that's kind of what this lecture is aimed at. Okay? All right, so first let's start very basic. So computational fluid dynamics. And so you probably heard the acronym CFD for short. Okay? And so what that refers to is just using a computer which often ends up being high performance computing, to simulate fluid flow, right? And so the way it works is that it takes your governing equations, and which in this case are the Navier-Stokes equations, and it solves those equations on an arbitrary geometry. Okay, and so here you can see this is a fun example that I found on the internet. And so what they did was they used CFD to model the airflow that goes around an elephant. Okay, and so in the computer they created a CAD model of an elephant, and they used CFD to model the airflow around it. And so basically any material that's a fluid can be simulated with CFD. And so, when we think of fluids, I think most people think of water, they think of liquids, right? But fluids can also mean gases as well. And so, aerodynamic simulations that Boeing uses, that NASA uses, they use CFD for that. And you can use CFD for fun stuff like this as well. Okay. And this is really useful because, as we know, the Navier-Stokes equations are very, very difficult to solve, right? So we can only really solve them by hand in very, very niche situations. And even then, it's still kind of an ordeal just to get a solution, right? We just spent the whole last week doing that for just a simple unsteady case, right? We spent, I think, a lecture, almost the entire lecture, learning about Bessel's equations and things like that, right? And so when you get to anything that's even more complex than that, it becomes basically impossible to solve by hand. Okay. But with computers, one thing that computers really do well is that they can do calculations super, super fast. And so, computer could probably complete, not even kidding, probably a million calculations in the time it takes a human to solve one. Okay. And so CFD leverages that fact, right? To produce a lot of really cool things. And so there's a lot of CFD codes out there. So you've probably heard of some of these. So probably the one that a lot of people know about is ANSYS, right? So ANSYS is the finite element software. And so with ANSYS, you can run CFD. Another popular one that's open source, and so open source means it's free, is OpenFOAM. Right? So OpenFOAM is actually one I've been trying to learn myself, although I haven't got too far with it. There's another one out there called StarCCM. I know that one is specialized for aerodynamics specifically. And so that one's used for turbulence modeling. That's kind of all I know about it. And of course, we have Cymbascular, and so that's the one we're going to be using in this class. And so Cymbascular is kind of it's a CFD software, but it's specialized specifically for blood flow. Okay. Okay. All right. So where is CFD applied, right? And so let's talk about some of the applications. So basically, any kind of engineering situations, or even just everyday situations where you have fluid flow, you could use CFD to run a simulation. Okay. And so I have a couple pictures here. And so, the one that you see kind of at the top is they use CFD to perform basically weather modeling. Okay. And so what you see here are a bunch of buildings in a metropolis area. And so I actually believe this is Oklahoma City, I want to say. And what they did was they used CFD to model all the different wind patterns going around the buildings. Okay. And this kind of information is actually used for urban planning, just to make sure that, the buildings are, they don't create, really complex wind patterns, that, the drag on the buildings is sufficient, that the buildings are going to be okay, right? Because depending, as you can imagine, these high-rise buildings, they affect the wind patterns quite significantly. So you want to make sure you minimize that impact as much as possible. And so CFD modeling can be used to actually, plan out a city, just to make sure that, you don't create like a mini tornado inside your city accidentally. Okay. And on the bottom right there, you have some kind of manifold device. I actually forgot where this one's from, but you have basically flow and pipes that are going into this machine. So I believe it's from an engine of some kind, but I forgot exactly. And so some other applications where you see CFD used a lot. Number one is aerospace. So that's probably the biggest customer for CFD. And so anything that involves a very high speed vehicle flying through the air or flying through space, it's going to be interacting with fluids quite a bit. So airplanes, rocket ship propulsion, CFD is used at kind of almost every single level of every space. Okay. Next, we have weather modeling, which we just went over an example for that. Okay. We have industrial manufacturing, and so things like like if you're doing plastic manufacturing, you're doing some kind of press mold. That counts as a fluid flow, and CFDs are used to kind of design and optimize these devices or design these machinery. Okay. Of course, we have biomedical, and so of course that's the subject for this class. And so we have cardiovascular flows, which consists of blood flow. But we also have airflow as well. So I actually have a colleague that uses CFD to model airflow in the lungs. Right? And so she uses that to model kind of lung disease in like smokers and things like that. Right? So super cool work. Another application is HVAC. So HVAC stands for heating, ventilation, air conditioning. And so, of course, there you have an engineering device with a lot of flow of air. And so, of course, CFD could help in designing those things. Right. CFD is also used in thermal engineering. And so anytime you have any kind of convection heat transfer or heat transfer to a moving fluid, then CFD can be used there. And of course, automotive as well. So, if you ever look inside an engine, there's tons of moving fluids going, all over the place between oil, like motor oils, coolants, gasoline, right? And so you need CFD to kind of model these things. Okay? And so, CFD it's used a lot, and you'd be surprised at all the applications that it has. Okay. Any questions on this so far? Okay, and so how do we run a CFD? And so, like I mentioned, there's a process that you have to go through to run a CFD. It's not a magic button. And throughout all of the steps here, there are chances for you to make mistakes. And so, even as a user, right, not even as a developer of CFD, there's a certain amount of knowledge that you have to have in order to use it properly, right? And so, these are kind of what I define as kind of the 7 steps to running a CFD or any kind of computational simulation, right? And so in this presentation, we're going to go through all 7 of these steps, right? And so first we have to define the problem. Next, we have to model the geometry or domain. And luckily for you guys, because on the midterm project, you guys are done with this step already. And so, you guys have already modeled your geometry. Okay. Next, we have to produce a mesh, and we'll talk about what that means later. We have to apply boundary conditions. We have to specify some additional solver parameters. Then we run the simulation, and then we post-process and analyze. Okay, so let's start going through these steps. All right, now step 1 is defining the problem. And so I would say this is probably the most important step that you can do whenever you're running any kind of simulation. Okay, and so for those of you who have run simulations before, you probably know that running a simulation to analyze an engineering problem, the mindset is very different from when you're kind of working things out by hand, or if you're running an experiment for it, right? You're putting a lot of trust in the computer to kind of handle a lot of the mechanics for you, right? Because if you're working on a problem by hand, you kind of see every single step of analysis, if you kind of know what I mean. So you write down all the equations, you perform all the calculations, and you see kind of the solution evolve as you produce it. For simulations, you're not really babysitting the analysis, like, in that sense. You're kind of the mindset is you kind of have to set it up for the computer, and then the computer is going to do most of the work for you. Okay? And so your mindset is a little bit different. So you have to think in terms of, let me set up this problem for the computer, and the computer is going to do the work for me. Okay. And of course, if all your effort is going to be put towards the setup, then you have to make sure that you define the problem really well. Okay. And so, defining the problem is a very kind of vague process. And so, the way I like to think about it is to think about it in terms of these kinds of questions. Okay. And so first of all, you can ask yourself, what is the physical domain of the analysis? Right. So what are we running a simulation on? And so for all of your guys' project, as an example, the domain for your analysis is going to be the anatomy of your blood vessels, right? And so those are the CAD models that you've already developed in Vascular. Okay, so that part's already kind of done. Next, you have to ask what kind of physics are relevant to my problem, right? Which seems obvious, right? And so a lot of times people just run a fluid simulation, so they want to run CFD, or they want to run structures, right? Or they want to run thermal. But sometimes there's more than one type of physics involved. Okay, so let me give you an example. And so for your guys' projects, you're going to be running a CFD. But you're going to be running a rigid wall simulation, okay? And that's just kind of out of simplicity. But we know, right? We've already talked about quite a bit in this class that blood vessels are not rigid structures, right? So they have flexible walls that kind of breathe and kind of move, and that's how the wave propagation comes to effect. And so if you really want to do a really accurate blood flow simulation, you not only have to worry about the fluid physics, But you also have to think about the physics of the deformable walls too, right? And you start to think, I have to not only have to do fluids, but I have to include structures. And those two domains have to interact with each other. So I have to include things like fluid structure interaction. Okay? And so very quickly, you start to realize that a lot of practical problems out there actually use what I call multi-physics. Okay? And so taking a second to think about, what kind of physics are involved is really important because that's going to change what you do in terms of the simulation. We won't worry about it too much for this class because this class we're just going to be running pure fluids, but it's something important to think about when you're running simulations outside here. Okay. All right, number 3 is to think about what kinds of equations govern the physics of your problem, right? And so for fluid mechanics we have Navier-Stokes. That's probably the most classical way to model fluid flow. But there's actually believe it or not, and we don't teach this in the classes. But there's more than one equation that models fluid flow. So Navier-Stokes was not the only one to model fluid flow, right? And there's another method that's actually used. I would say Navier-Stokes probably comprises about 90% of blood flow simulations. But there's another method. The name escapes me, but that's probably using about 10% of methods. But that's perfectly valid as well. And so, there's some advantages to using Navier-Stokes, and there's some advantages to using the other method as well. Okay. And so you have to think about, what kind of equation do I want to solve for this and adjust accordingly. And so those are all, those 3 questions are important for, first of all, define the problem. But I think the last 2 questions here are really important, when you're first starting to get into simulations. Okay. And so number 4 here is what information do I want to get out of the analysis? Okay. And so in other words, what am I trying to find out? Right. And number 5, what are some expected results? Okay. And so these informations are really important. And I want you guys to think about this, before you run your simulations for your project, right? And so a simulation is never just run just for fun, right? It's true that if you run a simulation, it produces, really nice graphics. And so, we can produce graphics like these, right? These look really fun, really cool. But, it's very rare that you actually do these for fun, okay? And so a lot of times as an engineer, the reason you're running the analysis or you're running the simulation is because you want to find out some specific kind of information, right? Something that you can't solve for, by hand calculations or by by experiments. Okay. And so as an example, right? And so we know that CFD is used a lot in aerospace, right? In aerospace, what they're interested in, when they're designing the airplane, is they want to find out, how much drag is there going to be on this airplane, on this wing design that they're making? How much lift am I going to generate, right? How much power is this airplane going to require? Right? Because airplane design is so complex nowadays, those are questions that you can't really answer with hand calculations. And so when they run their CFD analysis, they're specifically looking for, let me compute the drag on my wing, let me compute the lift, right? And so that's important for you to, to ask yourself. Okay. And so for blood flow simulations, it's going to depend on your geometry. It's going to depend on, for a lot of your projects, you guys are doing simulations on, cases that might have an aneurysm, maybe cases that might have high blood pressure, or maybe some cases that have like atherosclerosis. Okay. And so you have to ask yourself, what are the most important quantities that you want to find out? Okay. I would say for a lot of your projects, you're going to be looking for wall shear stress. Okay. And so that's going to be really important. And so, you want to make sure that you know how to get the wall shear stress out of your simulation. For some of you, pressure is going to be important. For some of you, the velocity patterns are going to be important as well. Okay. And so, for all your projects, think about, I want you guys to do a little bit of research about, what are some common diseases for the part of the body that you're modeling. And for some of you, you already have that disease, right? So for those of you who get congenital heart disease, you already know what kind of disease that patient has. And so, I want you guys to do a bit of research and looking up, what are the important quantities that have to do with this disease, and can we get this out of the simulation? Okay. All right, and then finally, I want you guys. It's always important to have some kind of prediction of what your results are going to look like as well. Okay, and of course that's hard to do when you're first starting out, right? And so when you're running your first few simulations, you're kind of thinking, I'm not really sure what to expect. but it is good to kind of think about. Okay. And I'll give you an example that I would say probably half of you guys will probably run into in this class. You're going to run your simulation and it's going to metaphorically blow up. And so what that means is that you're going to solve for velocities that are like, infinite, or they might even not compute, so you might get infinity, or might get not a number, right? Or you might get pressures that are undefined. And so those are results that are not correct, right? And so you can look at those results and immediately say, this is not correct, because, the pressure inside a person, there's no way for it to be infinity. And so it's always good, when you run a simulation, to look at the results and to perform a sanity check, right? And so you to look at the results and think, does this make sense? Does the result I'm getting make sense, or did I mess something up with the setup? Okay, it's very easy. It's very easy to run a simulation, get the results, and say yes, this is perfect, this is great. Right? But a lot of times that's not the case. And so even for experts, I would say. Even for experts, when they go to set out to run a simulation, they have to run it a few times just to kind of work out all the kinks, because there might be some issues that come up that they didn't expect. Okay. And one last tip that I have here, that it's sometimes it's helpful to just draw a quick picture by hand, just so that you kind of illustrate what you kind of expect from the results. Okay, so I spent a lot of time talking about this slide because I want you guys to really think about this when you're doing your problems. Okay, and so it's very easy to kind of get caught in just kind of going through the motions of running a simulation, but it's important to think about what problem are you trying to solve, and what are you trying to get out of the simulation. Okay, any questions on this? Okay. Okay, next step is to model the geometry. And so, like I mentioned, you guys have done this already. And so the next step to run a simulation after you kind of define the problem is to get a computer representation of your geometry. Okay, and so for most cases, this means creating a CAD file in some kind of CAD software, like SolidWorks is a popular one, or you can use Vascular, which is what you've done. Okay, but one important note that I want to make here. And, Vascular kind of does this automatically, and so you don't really have to worry about this. But if you are interested in doing CFD, based on a SolidWorks model, you want to make sure that you're actually modeling the correct part of the geometry. Okay, and so what I mean by that is that when you run CFD, you want to create a CAD model for the regions where the fluid is actually going to flow. Okay, and so this is kind of an opposite thinking when people are generating CAD models normally. Okay, and so I have a very classical example here. So if you're tasked with creating a CAD file for a pipe, right, you might make something that looks like the top image right here. Right? And so you model basically the solid part of the pipe, right? And so maybe you're getting some pipe from Home Depot, some PVC, right? And so you want to model that in your CAD software, and so you create a model of what I call the solid part of the pipe, or the thickness of the pipe. Okay, that's not going to work for CFD, because the fluid is not going to flow in the solid part. The fluid's actually going to flow in the cavity between, right? And so when you create your model for CFD, you should actually create a CAD model of where the fluid is going to go. Okay, and so to properly model the flow inside this pipe, you need to create a CAD model of the cavity, right? And so it's a little bit hard to tell, but if you kind of took this cylinder right here, the solid cylinder, it would fit right inside this pipe right here. Okay, and so the bottom would be the proper way to simulate fluid flow in a pipe, and not the top one. Okay. Okay, so the next step is meshing. Okay, so I think this is a fun step, because I think these are the images that people like to look at and like to share, right? Okay, and so after you create your geometry in the computer, the next step is to actually break up that geometry in lots of really simple shapes. Okay, and so what you can see right here is that we have a CAD model of a fighter jet. Okay, but we've broken it up. Okay, and so we don't have just one big fighter jet CAD model, right? We've broken it up into all these little triangles and all these little tetrahedrons, okay? That together, when you put them together, comprise the geometry, okay? And so in other words, think about, I think one good analogy is that you take your geometry, and if you were to say, if I were to build this geometry out of Legos, that's kind of what it would look like, right? And so you basically define all the Legos to make up geometry. Okay? And so this process of taking a complicated geometry and breaking it up into a bunch of simpler shapes is known as meshing. Okay, and we give it that name because visually it kind of looks like you put a mesh grid or mesh kind of manifold on top of your geometry. Okay, and so the reason we do this is that if you think about it, you can run CFD on almost any kind of geometry, right? And so because every geometry is different, it's really difficult for a computer to solve. Even for computer, it's really difficult for them to solve complicated equations on these complicated geometries, right? And so in order to make it work, what you have to do is you have to break up that geometry into a bunch of, much simpler shapes, okay? And so, when I say simple shapes, I really mean simple shapes. And so I mean things like triangles, I mean things like rectangles, okay? Right, basically, all your favorites, all the classics from kindergarten, right? So that's what you need to think about, right? And so in 3D, you would have things like boxes, okay, and a four-sided prism or four-sided pyramid. Thank you. Four-sided pyramid known as a tetrahedral. Okay. And so tetrahedrals is actually the ones that we're going to use, and tetrahedrals have a lot of really nice properties. Okay, I'd love to get into this more because I think meshing is really fascinating, but we don't really have time for that in this class. And so, just know that in order to run a simulation, you have to perform a mesh on you have to get a mesh on your geometry. Okay, and the shape of the elements is important because that's kind of what allows you to run the simulation. Okay? And so again, we're not going to get into the specifics, details of meshing, but it's important to know kind of generally what it is. But it's also important to pay attention to the number of elements and nodes that get generated in your mesh. Okay. And so when you mesh your geometry, and you'll see when we get to this in Vascular, you can specify the size of the elements, right? And so let's say that you have kind of a complicated geometry, like this, right? You can choose to have really big elements, right? And so let's say that we break this up into elements that might be this size, okay? Right, and so there's a specific setting for it. You'll say that I want my elements to be 0.1 centimeters big, right? And so that defines kind of the edge length of the mesh. Or you can make it even smaller. And so let's say that you define your mesh size to be 0.01, right? And so you end up with a much finer mesh. It's a terrible drawing, but you guys get the idea. Okay. And so what's the difference, right? And so, what's the difference between getting a mesh with a lot of elements versus a mesh with not so much elements? It matters for the cost, okay? And so generally speaking, the more elements that you have in the mesh, the more elements and nodes, the more computationally expensive your simulation is going to be, okay? And when I say expensive, I don't mean money, right? So, you guys don't have to pay anything for this class, okay? What I mean by expensive is time and computing power, okay? And so the more elements that you have in your mesh, the longer your simulation is going to take, and you might need to devote more cores or more CPUs to run the simulation, okay? But for that higher cost, you also get something nice in return because generally the higher number of elements that you have, the more accurate your simulation is going to be. Okay, and accuracy is good because the more accurate your simulations are, the more reliable it's going to be. Okay? And so there's this trade-off that is real. Whenever you do any kind of computational work, is you want to ask yourself, how much accuracy do I want for the simulation versus how much time am I willing to wait? Okay. And the tempting thing, or maybe it's not tempting, maybe it's just me because I'm weird, but the tempting thing is to just, kill your geometry with elements, right? And so to really kind of push the limits. And so I remember the first CFD simulation that I ran when I was a grad student, I ran it with, I think 16 million elements, right? And so I just made the elements really small. And I'm like, hey, it's a supercomputer, it can do it, right? Well, it turns out I hogged up the whole supercomputer and no one else could use it for like an entire day, and everyone got mad at me. Okay, so and so you want to be careful. Okay, and so there's a trade-off, right? And so there's a sweet spot between them. Okay? And so an analogy that I'd like to think about in terms of this trade-off is think of a resolution of a digital image, right? And so when you're getting an image, from let's say someone took a video or someone took a picture of something, right? We've all seen it, right? And so someone took a picture of something really cool, and so they send you a picture, but it's like potato quality, right? And so the resolution is really coarse, but the file is really small because it's a really coarse quality, right? But if they took that picture with really nice camera like a DSLR or something, right? It's going to be beautiful. It's going to be a beautifully rendered image with lots of pixels, but the file is going to be like 500 megabytes or something like that, right? And so I think that's a good analogy for you to always keep in mind in terms of your mesh, right? And so you can give it more elements, right? But that's going to come at a cost of more computing power and more time. Okay. And so, of course, the question that everyone asks is, what's an appropriate number of elements for your guys' projects? I would say, for your guys' projects, I would stay in the ballpark of around 500,000 to 1 million elements, depending on your geometry. Okay. Okay. And so if you're in that ballpark of the number of elements, you're usually, I would say your results are accurate enough, right? So I would say accuracy is not really concerned. But you would have to run these on the cluster, okay? And so you can try to run these on your computer, and if you have a really nice computer, it might be able to run in a few hours, okay? But generally speaking, if you're getting into this territory here, you would want to run these on the supercomputer. But I think, and one thing I want you guys to do for your projects too is I want you guys to test the simulations on your computer, right? And so that's possible, but if you're going to run a simulations on your computer, I would say stick to around 100,000 elements. Okay. So this is for your PC, for your computer. Okay. And so if you keep the element count within 100,000, you can run that simulation on your computer, and you can use that to kind of debug some issues. Okay. And so, the idea is that, you start, and this is true for any kind of computational work. You start with a fairly coarse mesh. You start with something, fairly small. You run it on your own computer. You debug most of the issues. Then once you feel confident in all the settings, all the boundary conditions, then you increase the mesh and you ship it off to a supercomputer. Okay. Because usually, and for this class, you don't have to worry about it. I've secured enough resources, but generally speaking, the time and the amount of resources you can use on a supercomputer are pretty limited. I think nowadays it's easier to explain because I think everyone's kind of familiar with crypto and NFTs and things like that, right? And so to perform these kinds of calculations, it takes a lot of power, right? It takes a lot of time. It's not going to be, well, okay, it depends, but there are some simulations that can approach kind of the level of computation that's needed for NFTs and crypto. But we're not going to be running on ginormous, GPU clusters here, but the amount of computation that it takes is still significant. So you want to make sure that whenever you use a supercomputer, that you're kind of responsible. Okay. But we'll kind of go through this as we get closer to that. Okay. Any questions on meshing? Okay. Yeah.
Do certain shapes. Do you get like a higher accuracy with certain shapes, or does it come with the full setting?
Yeah. So the shapes do make an impact for sure. I would say the element size is probably the most predominant factor in terms of accuracy. But certain shapes are generally better than others as well. And so the one that we're going to use, the tetrahedral, I would say this is probably actually the worst in terms of accuracy compared to like the box. Okay. And so, but what's nice about tetrahedrons is that you can use tetrahedrons to comprise any geometry, right? And so tetrahedrons have this property where like you can take any arbitrary geometry and you could fill it with tetrahedrons, no problem. Okay? With a box, that's not necessarily true, right? And so there might be some geometries out there where you can't put a box inside them. But for the cases where you can put boxes everywhere, that generally leads to a more accurate simulation for the size that you have. But it's still kind of an area of research right now because generating good, these boxes, the technical term for them is hexahedrals. And so generating good hexahedral meshes is still very much kind of a big area of research right now. And I don't think anyone's really figured it out, for an arbitrary sense, but people are researching it. So for now, tetrahedrons are still kind of the standard just because they're just really easy to use. But hexahedrons, once the technology gets better, I think probably you'll see those a lot more. Okay. And so at this point, we've defined our problem, we've created our geometry, we've meshed, right? And so maybe we have a coarse mesh, fine mesh. And so the next step is actually to start specifying the physics, okay? And so to that end, we have to define these things called boundary conditions. Okay? And so even though the computer knows that, for this particular model, maybe we're solving the Navier-Stokes equation, okay? But in order to complete the solution, in order to close the solution, we have to define what the solution looks like at the boundaries of our domain, okay? And so these are called boundary conditions. And so if you think back to, think back to EGME 308 or maybe, Math 258, right? When you were solving differential equations, you kind of solved it in 2 steps, right? So the first thing that you did was you solved, the general solution, right? And so the general solution had arbitrary constants involved. But eventually, in order to get the full solution, you had to apply, boundary conditions onto it. Okay? And so, that same principle applies for simulations. But the way that we apply them is not mathematical, they're just purely physical instead. Okay? And so for CFD, there are 2 categories of boundary conditions that we have to specify. And so we have to specify boundary conditions on the inlets and outlets. Okay. And so I'll kind of group those together. And we also have to specify boundary conditions on the walls as well. Okay. So let's start with inlets and outlets. Okay. And so inlet and outlet boundary conditions, I kind of grouped them together because these are basically the regions in the model where fluid is going to pass through. Okay. And Vascular actually makes this they make it really clear for you, right? And so if you remember, when you did your modeling step in your midterm project, and you looked at your list of faces, right? So if you remember that, I think most people kind of had the issue of non-intersecting faces, right? If you remember, Vascular kind of classified your surfaces as either a cap or a wall, right? Cap, and wall. And so that actually has significance. And so a cap is corresponds to the end caps of your model, right? But we know that blood is going to be flowing through those caps. And so the types of boundary conditions that we're going to apply on your caps are going to be inlet or outlet types, okay? And so generally these inlet and outlet boundary conditions fall into two categories. So we have one type of boundary condition called Dirichlet, right? So Dirichlet is the technical term for it, but for the physical term for CFD is a flow type boundary condition, okay? And so for these type boundary conditions, you're basically specifying the amount of flow rate that's coming in. Okay? And so think back to our lump parameter models or even our 1D equations, right? And so we've seen flow rate kind of show up quite a bit in this class. And so flow rate defines how much volume, the rate at which the volume of blood is being pushed through the model. Okay. And so we can use that as a boundary condition. And so it's just like we did for lump parameter models. Okay. And so typically speaking, your flow type boundary conditions are applied at your inlets. Okay. All right. And so besides that, we also have pressure type boundary conditions. And so pressure types, these are typically your outlet boundary conditions. Okay. And so we know pressure is also a big part of the cardiovascular system as well. And so the way that we can specify that on our models is as pressure type boundary conditions. Right? And these are typically used as outlets. And so Vascular actually uses a very special form of a pressure outlet boundary condition called a resistance. Okay? And so resistance, think about our Ohm's law for resistors. Okay? And so the resistance kind of specifies a relationship between the flow and the pressure. And so, I'd say the most classical way to apply a outlet boundary condition is through pressure, but Vascular does it a little bit more specialized for blood flow. Right? And so we'll go through, how to specify a resistance, once we do our tutorial. Okay. Okay. And so the other type of boundary condition that you're going to specify are wall type boundary conditions. Okay? And so wall type boundary conditions specify the velocity solution on regions of the model where flow is not supposed to pass through. Okay. And Sylvester names these types of boundaries walls. Okay? And so in addition to the caps, you saw that there were wall type boundary conditions. And so the most common type of wall boundary condition is a simple no slip boundary condition. And so all that means is basically that, all the velocity that all the fluid that touches the wall has to have zero velocity. Okay? And so this essentially makes it so that, even though it's called a no slip boundary condition, right, because our walls are not moving, a no slip boundary condition is basically the same as a rigid wall assumption. Okay. Oh, I mentioned that in the next bullet point. Okay. And so for all your simulations, just because they're a lot easier and a lot simpler to set up, they're going to be mostly rigid wall, or at least I want you guys to start with the rigid wall simulation. Okay. And so it's certainly possible to do a deformable wall simulation. And so to basically run a CFD where the walls can move and respond to the flow. And if you're interested in doing this, you're definitely welcome to do so for your project, and I can work with you individually to set that up. But they are quite a bit more complicated to set up. And so I will say that if you're interested, I would say go for it. I'm never going to stop you from pursuing something that you're interested in. But just be aware that they can be difficult. And by difficult, that means that you're probably going to run a few of these simulations, and they're all probably going to fail to some degree. Okay, and so they're a lot more tricky to set up, and so that's why I don't require it for the project. But you can still do it if you want. And what I've heard, is that we've spent most of this class talking about how important it is for wave propagation and things like that. And then to not be able to model that in your final project is a little anticlimactic, but the project still has to be done, practically speaking, in the time that we have left, and so that's why I kind of limit it to just rigid wall simulations. Okay, so any questions on boundary conditions? Okay. Okay, and so the next step is to specify solver parameters. And so, there's a lot of other parameters that you have to specify, and I didn't want to break this up anymore, but there's a lot to specify. And so, probably this is going to be the part that's kind of most confusing to people, just because we're going to be specifying a lot of these things, but they're important for us to specify. Okay. And so, when I say solver parameters, these are parameters that have to do with the simulation itself, okay? And so what we've done so far with the boundary condition is we've kind of specified the physics of the situation, but the solver itself, how the CFD actually runs, there's some more settings that you have to specify as well. And so some of these are more important than the others, and so we'll focus on those ones. And in fact, this is only a small slice of all the different settings that you can do. And if you're kind of looking at this list for the first time without any guidance, it's kind of overwhelming, because it uses a lot of jargon and a lot of numbers that you have no idea what they're doing. And so I would say this kind of section is kind of the most is the biggest benefit to having someone kind of show you how to run CFD instead of trying to learn it on your own. Because if you try to do it on your own, then you can easily be overwhelmed with these settings. Okay, so I have a list here, and so let's just kind of go through the list, okay? And so first of all, we have the fluid properties, and so this is probably the simplest one. And so we have to specify the density and the viscosity of the blood, okay? Or whatever fluid you're trying to simulate, okay? So that's pretty straightforward. And so those you can just simply look up in a table based on whatever fluid that you're simulating. And number two, you have to specify the time step size. So this is really important, actually. And so the way a CFD simulation works is that think about it as if the CFD is kind of producing a video or an animation of your flow, right? And so you have your geometry like this, okay, and you're going to simulate the flow going through it, and the flow most of the time is going to change with time, okay? And so the simulation ultimately is going to be creating an animation of how that flow is running through the model, okay? And so think about when you're creating an animation, when you're creating a video, one of the things that's most important is to specify the frames per second, or the FPS, right? And so the amount of frames that you have per second, I think the standard is probably 30 frames per second, or there's 60, right? So I think in terms of video games. And so basically 30 frames per second means that, across 1 second, you have 30 different frames of motion that are kind of blended together in that second to create, the illusion of something moving, okay? And so simulations, you have to specify that as well, right? And so you have to specify, how finely you want the time domain to be discretized. And the way you do that is by specifying the time step size, okay? And so I think this image right here kind of shows it really well, okay? And so in this particular image, we have a time step size of 0.1 seconds, okay? And so that means that every frame that the simulation, is simulating, the amount of time that separates each one is going to be 0.1 seconds of real physical time, okay? And so with a time step size of 0.1, that means you have 10 frames per second. And so, over the course of 1 second of, if you're going to simulate 1 second of action in your simulation, there's going to be 10 frames in between them because of a time step size of 0.1, okay? And so think of the time step size, very similarly to how you thought of the mesh size, okay? And so generally, the smaller your time step size, the more accurate your simulation is going to be, right? And so because the amount of time that separates each frame is really, really small, okay? But it's going to take you longer to run the simulation, right? Because generally speaking, you're going to run your simulation for a set amount of real time, right? And so, let's say that you want to run your simulation and you want to simulate 10 seconds of blood flow, right? That's usually what you're specifying before you start, right? So you basically want to see 10 seconds of action, okay? And so with 10 seconds, if you use a time step size of 0.1 second, okay, and usually the symbol for time step size, we give it the symbol delta t, okay? If you give it a time step size of 0.1, that means you're simulating basically 100 frames, right? And so, you're going to have 10 frames per second. And so you're simulating, 100 frames. You can think of it like that, okay? Okay. And so your simulation is going to take, 100 steps for it to finish, okay? And the time to simulate each frame is about the same, okay? All right. But let's say that instead you want to run a simulation with a time step size of 1 millisecond. Okay, so you can do 0.001. Okay. Right. And so with a time step size of 1 millisecond, to simulate the same 10 seconds of action, it's going to take you not 100 frames, it's going to take you 10,000 frames. Okay. Right. Okay. Yes. I can multiply by 100. That's good. Okay. And so, of course, simulating 10,000 frames is going to take 100 times longer than your 100 frames, right? And so, you have to judge, if you can stomach that cost of 100x. Okay? And I think, when you're first running simulations, I think you don't really get too much of an appreciation for this. Because I think, because I know that when I was a student, when I thought of simulations, I thought of, hey, I'm running this MATLAB script. And it only takes me, 3 seconds to run the MATLAB script in the worst case, right? And so if I wait 100 times that, then I'm waiting 300 seconds, which is 5 minutes. I'm like, yeah, that's no problem. I can wait 5 minutes, right? I can go, I can go to the bathroom. I can go make a hot pocket, no problem. But when you're doing these kind of high performance simulations or high fidelity simulations, to produce 100 frames of data, this might take you maybe like 3 hours of computations. Okay? And I'm not even joking. So that's, that's actually still pretty modest. And so if you increase this cost by a factor of 100, right? So instead of 3 hours, you're waiting 300 hours, right? And so how many hours in a day? There's 24 hours in a day, right? And so you're waiting what, like almost 2 weeks for your simulation results. And so that's a big difference. Okay. And so again, again with the mesh size, you have to be really thoughtful and really careful about how you specify the time step size because it can get out of control very, very quickly. Okay. But of course, when you're first starting out, you kind of have no idea what to specify for the time step size. And so, for your guys' simulations, I would say a good time step size to start with is 10 milliseconds. Okay? And so this is a good one to start with, and that's what I'm going to tell you guys to use, for your first simulations. Okay. Because the time step size that you end up using, it depends on the problem and it depends on the physics. And so for blood flow, 10 milliseconds seems to do pretty well. Okay. And so that's kind of a good place to start. Okay. And so after the time step size, we have to specify the number of time steps. And so the number of time steps, you can think of the number of frames in your animation. Okay. And so, just going back to our example, right? And so let's say that we want to simulate, 10 seconds of action, right? And so 10 seconds divided by 10 milliseconds, right? This is going to be 1,000 frames, okay? Right? And so if you wanted to run a simulation for 10 seconds of time, with a time step size of 10 milliseconds, you would say the number of time steps is going to be 1,000. All right, and so those two settings combined, I would say those are the two most important settings that you have to specify. They combine to say how long your simulation is going to run. Okay. All right, number four is a setting where you can specify how often you want to save your results. Okay. And so by this I mean how often do you want to save a frame? Okay, because a lot of times if you're running with 10 milliseconds, it's kind of overkill to save results every single frame. Okay. And so maybe you only want to save the results every 10 frames or every 50 frames, okay? And this is something that's also kind of misleading too, because I remember when I first ran CFD, I just set this to be 1. I'm like, hey, we're doing all the work, let's save every frame, right? Why are we throwing out so many frames? But it makes a difference because the more frames that you save, the more space it's going to take up on your computer. And so that 16 million simulation I was telling you about, I saved it every single frame. It took up about how much was it? It was about like 600 gigabytes of data on the cluster, and I got a very stern talking to by a lot of people. And so CFD produces a lot of data, and I can't really understate that. It produces a lot, and so you want to really be careful about how often you save your results, and think about how much is really necessary for you to perform your analysis. Okay? And so for your guys' simulations for your projects, a good starting value would be something like 20, anywhere between 20 and 50. Okay, and so you can save every 20 frames or every 50 frames. That's going to keep the cost down well. It's going to save your laptop from a lot of from taking up the entire hard drive. Okay. And so that's setting number 4. And so setting number 5, I've kind of grouped it all together. And so there are other settings in CFD called linear solver settings. Okay. And to get into this would require probably a graduate level class in simulation technology. And so, I'm not going to get into these, but I just want to make you aware that they exist. Okay. And so think of these as kind of some fine tuning about how specific features in the solver work. Okay. Because when we think about CFD, we think about it as kind of one big entity, but it's really a bunch of smaller parts kind of working together to kind of make it work. Okay? And so these linear solver tolerances or linear solver settings are kind of some fine tuning, settings that you can specify to kind of tinker with those features. Okay? But generally speaking, if you don't know what you're doing, then the best thing is to not touch these at all. Okay, and so I want to make you aware of them, just to tell you to not touch them. Okay, so just kind of leave them alone, unless I kind of tell you to do something different. Okay, but a lot of times, these settings will have default values, because generally speaking, you kind of need a graduate degree in computational physics or mechanical engineering, and to take specific courses to really understand what these mean. And so most people are not going to have those, and so the developers of a lot of these softwares, they put default values there that work that are generally good for most cases, but there are some niche situations where you might want to change them. But again, they take a bit kind of more expert information, and so I'm making aware of them, but don't touch them. Okay, and so that was a lot of info. So are there any questions on this? Okay. All right, and so that's all the setup. And so now we go to the fun part, or not fun part, depending on your perspective, right? And so the next step is to run the simulation, right? And so you've done all the hard work now. So you set up the problem, you've specified the boundary conditions, you specified the solver settings, and so now you basically say, Jesus, take the wheel, or in other words, computer, take the wheel, okay? And so this is either the most exciting part or the most boring part, depending on kind of how many you're running. Okay. And so basically, this is in the one sense, this is exciting because you're kind of running a CFD, and that's kind of exciting in its own sense, right? And so you're kind of waiting for the computer to chug along. But it's boring in the sense that you can literally do nothing during this time, right? And so you kind of just have to wait for the computer to finish it to run. Okay? And so if you're running this on your personal computer, then, if you have a coarse enough mesh, like we talked about earlier, it is able to run, but it is going to probably, eat up your entire CPU, your entire processor on your computer. And so just be aware of that. And so, a simulation might hog up all your computer resources, and you can't play games while it's running. Okay. But it is possible. Okay. But most people, because of the cost for these simulations, they run them on supercomputing clusters. Okay, and so if you're not aware of what a supercomputing cluster is, it's basically what you see in the movies. And so you basically have all these computers kind of stored in kind of a rack kind of mounted thing like this. Okay, which are dedicated to run computation. Okay, and the nice thing about this is that with the supercomputing cluster, for one that looks like this, right? So a typical server room. You literally have, tens of thousands of cores at your disposal. Okay? And so typically, when you're buying, let's say you're buying a new laptop, you're buying a new computer, you think, yeah, it has 4 cores, it has 8 cores, yeah, that's a powerful computer, right? But supercomputers kind of take it to the next level. And so, when you mount computers like this, you can have tens of thousands, and some of the bigger ones have like over 100,000 cores at your disposal for you to run simulation. Okay. Of course, it's not just for your use, and so a lot of people are using it at the same time. But you can dedicate 48 processors, 100 processors, 200 processors to your simulation, without really compromising the rest of the cluster. Okay, and so that's going to be exciting, and that's something that you guys I'm gonna be able to get for you guys as well. And so for your projects, I've done all the setup already. I'm going to give you guys accounts on a national supercomputer that you can run your simulations on. Okay? And the one that you guys are actually going to be running on is actually in San Diego. So it's a machine called Expanse. Okay? So that's going to be really cool. It's going to be really cool in concept, but it's going to be really boring in practice because you're going to log onto the website, you're going to run your simulation, and you're just going to wait, and then you're going to download your results. Right? And so it's a lot more exciting in theory than it is in practice. Okay? Okay, and so depending on the size and nature of your simulation, it can take anywhere between a few minutes, right, for a really simple job, to several weeks of running, right, even on a supercomputer. Okay? And so the variance on this is huge. So for your guys' simulations, I don't think, if you're using a supercomputer, I don't think the simulation is going to take more than an hour. I would say, an hour is probably going to be the top. Just because you guys are running fairly straightforward simulations. But they can go. Okay, and I will say something funny too, that this image right here, I think this is what people imagine when they think of clusters and supercomputers and hackers and things like that, super hackers. But I will tell you, there are literally 0 supercomputing clusters in America, around the world, that look like this. And so this looks really nice and really cool, like from a Hollywood set. Yeah, none of the real ones look like this. They're a mess of wires, and there's people everywhere, and there's it's really hot and uncomfortable because you have all these computers running, and it's just generally a mess. There's like a really depressed IT person somewhere in the back, and so it's kind of depressing. So I think about the scene from I believe it was The Martian, that Matt Damon movie. And Donald Glover kind of plays this character where he's like kind of the computer nerd, and he runs simulations on the cluster, and he's like, oh, let me run this simulation on the cluster. And so he plugs in his flash drive, he does like, right? And the cluster was like, your calculations are correct. And Donald Glover's like, yes. And I'll tell you, that never happened. So I got so upset at that. I'm like, like, what? And then, and my wife got really mad at me. She's like, shut up. So it's not like that. Okay, so it's not as cool as Hollywood makes it out to be. So this is very much a Hollywood rendering. So this is not what a real cluster looks like. Okay, and so after you run your simulation, and so the next step is to post-process. And so this is probably the part that's more exciting because your simulation is completed. Hopefully it was successful. And so at this point, you can go ahead and download your results, and you can start to analyze them. Okay. And so this is where you actually produce, a lot of the really cool videos, a lot of the really cool, figures that you've probably seen up to this point, right? And so maybe something like that, okay? And so, this part, we're going to spend some time on, and it's hard to kind of explain this part, without really, going into some vascular, but this is where you see, so you ran your simulation, so you can start to see, what does the velocity field look like? What does the pressure field look like? What does the wall shear stress look like, right? And so this is where you would actually look at it. Okay, and so we're actually going to download another software that's used for this called ParaView, that has a lot of really nice visualization tools associated with it. Okay, and so at this point, it's important to check. So remember when we started today, we talked about how important it is to make some predictions or to have some expectations for what your simulation is going to look like, right? And so this is where you check. And so you check to see the pressure, right? So does this pressure make sense? Like, is it something physical? You check the wall shear stress. Does this make sense? Is it something physical, right? And so this is where you kind of check your results just to kind of make sure that you're on the right track. Okay. And so I also want to talk a bit about high performance computing. And so I've been kind of throwing that term out there a bit. But when people mention high performance computing, they specifically refer to the use of supercomputing clusters. Okay. Performing analysis or simulation, right? And so physically, they look like they look kind of like this. And so this is actually a real cluster. And so this is one of the bigger ones that we have in America. And so it's called Blue Gene. Gene, not genes that you wear, like gene, like DNA gene. Okay. And so this is probably taken, right after it came out. And so, it's really nice. The guy's really nicely dressed, and so, I guarantee 1 week later, it did not look like this. I can guarantee you that. I've been in these rooms. It's not comfortable. Okay. All right. And so and so I kind of alluded to this earlier. Most of the time, when you're running simulations on these, you're gonna remote access. Okay. So you don't physically go to the cluster room to run your simulation. You kind of upload the files to them from your computer. Okay. And so here at Cal State Fullerton, we do have a small computing cluster, an NSM. So the engineering school doesn't have one. Which is a travesty, but the NSM college does have one, but it's not nearly this big. So we have kind of a smaller one that's here. Okay. But even for that one, even when you're physically at the same location as the cluster, you're still going to log in remotely. Okay. Okay. And so traditionally, when you're using a supercomputer, you have to access it via a command line terminal. Okay. But that can be a little bit restrictive. And so, that would require, learning how to use a command line terminal, which kind of takes a while to use it. So, it's quite different. But, there have been a lot more user-friendly options that have been developed, one of which you're going to use in this class, which is called a gateway. Okay. And so the way the gateway works and the way I kind of set it up with a lot of my colleagues is that, there's a website that you can go to, and you upload your simulation files there, and then the website is going to interact directly with the cluster. Okay? And so you don't really interact directly with the cluster itself. The website kind of handles most of that for you. Okay. All right. And also traditionally, you have to do a step called compilation. So you have to compile your code on a cluster. But again, this is something I've done for you. Okay? But that's kind of typically how you would run it in a normal environment. Okay. So I believe this is the last slide. Okay. And so the last thing that I'll cover today is that, when you're running simulations on a cluster, you also have to set some settings for the cluster itself, okay? And so in particular, the two main ones that you're gonna have to set is how many processors do you want to devote to your simulation job? And how long do you plan on the simulation job, or how long do you think your simulation job is gonna take, okay? Because the way these clusters work, and so they don't just exist for one person's use, right? And so they're often shared among a bunch of students, researchers, faculty, a bunch of people are using these clusters because they take a lot of money, And so to construct, a decent cluster is probably it's going to run you somewhere, probably in the high 100,000s. So maybe 600, 700, 800,000. And some of the really big ones I know are, tens of millions of dollars of investment. Okay. And so they want to make that resource available to as many people as possible. So, you're always going to be sharing a cluster with somebody. Okay. And so the way they work is they kind of work on a reservation system. And so, what you say is that if you want to run a job on a cluster, you want to run a simulation, you're going to say that, I'm going to take up 50 processors, and I'm going to need them for 3 hours of time, because that's how long I think I'm going to run the simulation for. Okay. And so what that does is that that job request basically goes to, you can think of it as like the hostess for the cluster. And what that's going to do is it's going to try to fit your job in together with everyone else's at the same time. Okay. And so depending on how busy the cluster is, you might have to wait. And so you might have to queue, right? And so if the entire cluster is being occupied at the moment by a bunch of people, you're going to have to wait for your job to get through. Okay. But then once your job is in there, then that's when it can start to run. Okay. And so you have to be kind of prudent on this. And so, again, the tempting thing, especially when you're first starting out, is that, I want to run a simulation with 1,000 processors, right? But then that might not be practical. So, you want to kind of use the cluster on kind of on a need to use basis. So that's kind of the good way to be kind of a good citizen of the cluster. So, there's a lot of unspoken gentleman's rules, associated with using these clusters that, they don't say it in writing, but if you violate them, then people will get mad at you typically, right? And so let's talk about the number of processors first. And so generally speaking, when you choose the number of processors, when you devote more processors to your job, it's going to finish faster, right? And so as an example, so let's say that if you want to run a simulation, if you devote 24 processors to it, maybe it'll take 4 hours to run. But if you devote twice as many processors, 48, then it's going to run in half the time, right? And so, think about, the work is basically split between all the processors. Okay? And so, that's kind of one thing you could do. But you have to be careful because, there is a point of diminishing returns. Okay? Because if you devote too many processors to your job, then it actually doesn't, it might actually end up slowing it down depending on certain quantities. Okay. And so I have an analogy for you. So think about for a situation where you have to prepare 100 sandwiches, right? If you have 10 chefs, right? And each chef does 10 sandwiches, then you're going to finish 10 times faster than if you were to try to prepare them yourself, right? And so one person preparing 100 sandwiches would take, 100x time. But if you have 10 chefs, that's going to cut the amount of time down by 10. Okay. But if the task is to make 100 sandwiches, having 1,000 chefs is not really going to help, right? And so in fact, it might even be worse because you're going to have people that's bumping into each other over the kitchen, and you're going to have spills, and people are going to mad at each other, and their fights are going to break out, right? And so having 1,000 chefs is kind of overkill, and it might actually end up making your job take longer. Okay. And so the same principle applies for simulations as well. And so different people have different rules of thumb, but this is the one that I use. And so what I do is I base the number of processors on the number of elements that I have in the mesh. Okay. And so what I do is I take the number of elements in my mesh. And so let's say that I have, let's say that I have a million elements in my mesh. Okay. And then I take that number and I divide it by 20,000. Okay. Okay. And so we divide by 20,000. If we cross out all the zeros here, okay, it should give us about 50 processors. Okay. And so the ideal number of processors for this job is 50. Okay. So that's generally my rule of thumb. And so, but there is some flexibility with that. And so you can of course use less and use more. And so if you, as long as you stay within the ballpark of 50, you're going to be in good shape. Okay. And that usually gives you a kind of a good trade-off because, if you think about it, each processor is going to be responsible for a certain number of elements, right? And so you want to give the processor enough work for it to be worth it, to run the simulation, right? And so, just like the sandwich analogy. Right? And so as for the amount of time, right? And so that's one thing you also have to specify. I would say when you're first starting out, it's okay to kind of max out on the time. And so I think the maximum amount of time that you can specify on the cluster is somewhere close to actually like 12 hours or something like that. And so it's okay to do that when you're first starting out, because you don't really know how long the simulation is going to take. The good thing is that if your simulation finishes early, you only get charged for the amount of time that you actually used. And so it's okay to request a longer time, in case you're not sure how long your simulation is going to take. And so that's what I'm going to recommend for you guys when you're first starting out. Okay, and so I think that's the last slide. I can't click anymore, so yes, it is the last slide. Okay. All right, question. So do they run CFD on micro scale? Absolutely they do. Yeah, so they run CFD on every different scale. Yeah, and so I've seen simulations done in micro channels and kind of microfluidic devices. I've seen simulations done on capillaries, and so yeah, they run CFD on all scales. Yeah. All right, any questions on this before we wrap it up for today? Okay, all right, and so so we got actually through that faster than I thought. And so on Thursday, I think what we'll do is we'll do the tutorial, and so we'll do the workshop on how to do simulations in SimVascular. So I want you guys to have your midterm projects ready by Thursday, so that we can start setting up your simulation there. Okay. All right, so thank you guys for tuning in today. Hopefully the lecture today was interesting. So no math today, and so I kept my promise, right? And so remember to start studying for the midterm, because it is quite a lot of content. And if, as always, if you have questions or anything, just let me know. Okay. So have a great evening, everyone. Hope you guys enjoy the rest of your day, and I'll see you guys all on Thursday.
Yeah. Yeah, they're gonna show me something. I was like,
Okay.
yeah. All these pretty low.
Oh, sorry, David. Usually it's muted here because the projector makes sound. All right, go ahead.
Can you hear me now?
Yeah, I can hear you. What's up?
Okay, cool. Hey, so I messed up. I did the midterm review example thing, and it was late at night, and for some reason I read most comfortable instead of most uncomfortable.
Okay. that's okay.
I don't think that's gonna affect it's one student out of a lot.
I think you can redo the poll. And so I think I said it so that you can do it infinite amount of tries. But if not, I can go back and change it. But you should be able to kind of change your answers on the poll, I think.
Yeah, I tried to go on it, but there's no I can't click it. It just is what I answered, and I can't
Okay, yeah, I can go back and check it, but it's not that big a deal. And so typically, a lot of people kind of vote for the same things, and so
I just wanted to.
Okay, yeah, no problem. I mean, it's all anonymous too, and so I don't see who's
Thank you so much.
Yeah, no problem.
Thank you.
Yeah.